This is a video about section 3.3 in Stein's number theory book. It's an introduction to the RSA crypto system. And remember the Diffie-Hellman key exchange that was in the previous two videos? It had its drawbacks. In particular, it was susceptible to a man-in-the-middle attack. So what we'll move on to is an alternative crypto system that is still kind of cool because it uses a lot of this modular arithmetic stuff we've been playing with. And so it's rooted in some mathematics that, has been around since the 17 or 1800s, even though it's a very modern thing that we're talking about. So RSA is the crypto system we're going to talk about. Again, it's a public key crypto system, and it was developed by I think they're professors, Rivas, Shamir, and Adelman, and this was from 1978. That's when they introduced this here. And what we'll look at is just in this video, just kind of describe how it works. And I will pretty loosely follow the book here. I've kind of reworded the book and tried to draw some pictures too to make it a little bit more readable. But the big idea behind RSA here is we're going to try to construct a trapdoor, or in other words, a one-way function. I'll call it E. And E, you could probably guess, stands for encryption. And so E should be a bijection from X to X. So we still have our protagonist, Nikita, and her ally, Michael, and they want to send messages to each other, just like they've been doing in the previous videos. But they're worried that maybe somebody might intercept their message and read their communications. So what we're going to do is Nikita is basically going to build all the framework for the crypto system, and she's just going to share a little bit with Michael. And that'll give him an idea of how to encrypt stuff to send stuff to her. So here's how it'll work. And here's where I'm going to deviate. I'm really doing the same steps as the book in the following. So if you do read the book, steps 1 through 5, I'm going to number them a little bit differently and try to draw you some pictures too. There's my wonderful picture of Nikita. So what's going on in RSA? So the first thing that Nikita would do, and notice I'm not telling you anything about Michael. This is all Nikita right now. She would pick two very large primes, P and Q. Those primes P and Q would be her secret. So that would be part of her secret key. And what she does is she multiplies those together and she gets n. N can be public. I don't care if anybody knows what n is. So here's the idea. Phi of n then, if n is the product of these two primes, P and Q are relatively prime to each other, so phi of n should be 5p times phi of q, so p minus 1 times q minus 1. Now, since Nikita knows that n's factorization is p times q, phi of n is very easy for Nikita to compute. However, these are pretty gigantic numbers. It would be very, very hard for anyone else to compute. The same idea here with n. It's okay if everybody knows what n is, but if you know n, it's really hard to factor n. That's the big idea, is that it's still hard for us. Factoring has been a challenge for like 2,500 years, and it's still a really difficult problem for humans and computers to do. So right now, everybody knows n, but it's very hard to factor it. But it's very easy for Nikita to factor it, and it's very easy for Nikita, again, to compute what phi of n is. Essentially, she is the only one who knows what phi of n is. You can think of it that way, too. The next thing Nikita will do is she will randomly pick some integer e that's between 1 and phi of n, as long as e is relatively prime to what phi of n is. The third thing Nikita would do is she would compute a number d so that e and d are multiplicative inverses of each other modulo phi n. So d is the inverse of e modulo phi of n. And again, this is a computation that really only Nikita can feasibly do. Because again, Nikita is really the only one that knows what phi of n is here. So because Nikita is the only one, essentially, that knows what phi of n is, it's very hard for anybody to find out what this d is as well. And here's what we're going to do with this e and this d, these lowercase letters. Remember, e and d are just integers. So Nikita is going to build her function now. So here's where the trapdoor, one-way function that the book reference comes in. We're going to call one direction of it e, and so it'll be from z mod nz to itself, where n, again, is something that everybody knows. And what we're going to say is we're going to take a number. When I plug it in, I'm just going to raise that number to this e that Nikita picked above. So this E stands for encrypt. In other words, what we're going to see in another video is, how do I take strings of letters and turn them into numbers? That's called encoding again. So I'm not talking about encoding. Let's say, though, that you've got a message that is a number, say m. I'm telling you how to encrypt that message now. I take it and I raise it to the eth power. Now, anybody can see what this is. The problem is, if you can see what m to the eth power is, again, it's very hard to just see what m is. It's very hard for someone trying to intercept this message to see what m actually is. They can see m to the e, but it's hard to see m. Now, the inverse of this, we'll call it d, and you can guess d stands for decrypt. And what will it do? It'll just take the input and raise it to the dth power. And so what I'm suggesting is that when something is encrypted and then you compose that with this function, that's suggesting that m raised to the e times d power should just give you back m. And I'll show you why that is below. But so far, just to keep track of what's going on, the public key that everyone can know, whether it's Nikita, Michael, or someone bad, is n and e. It doesn't matter that everyone knows that. That's public information. The things that only Nikita knows are p and q, and therefore phi of n as well, and d. So that's Nikita's private key. That's information that only Nikita is privy to. And it's very hard for anyone else to figure out. Why are these functions e and d inverses of each other? So in other words, why is it true that m raised to the ed power should just be congruent to m modulo n? Now think about this congruence here is equivalent to this divisibility statement. I wish to show, in order to show this congruence, I wish to show that n divides m to the ed minus m. N divides their difference, right? We know that from like a proofs class, say. Now notice though that like if n divides this difference, then any prime in the prime factorization of n would have to divide that difference too. So in particular, n divides this difference if and only if the prime factorization, each prime in that prime factorization, p divides the difference and q divides the difference. And I'm only considering p and q because n is equal to p times q by hypothesis for this RSA stuff that we're doing. Now the argument that I'm going to show you, I'm going to try to show you that p divides this difference here. The argument to do that is equivalent to if I do it for q. So I'm just going to do it for p. And now I'm just going to translate one more time to say that p divides m to the ed minus m. I just need to show that m to the ed is equivalent to m mod p. So that's what I'm going to show. So all of this is just trying to say that to show this, it suffices really to just show this one. And the case for q is very similar. So without loss of generality, we'll just do it for p. Now, how should this work here? Well, there are two possibilities. I would love to use Euler's theorem, but I need to be careful. I need to make sure that m and p are relatively prime before I start trying to use Euler's theorem. And so let's get that out of the way. What if m and p are not relatively prime? That means they share a common factor, but p it's prime, right? So what could divide both m and p? Well, it would have to be p. And so in particular, p divides m. But then what happens when you reduce m mod p? Well, that would be 0. So what happens when you take that to a power, such as the power ed? Well, that would still be 0. That would just be 0 to the ed, which is 0. So what did we just show? M is congruent to 0, so is m to the ed, therefore they're congruent to each other, which is part of what I wanted to show. So case 1 is done. If m and p are coprime or relatively prime, whichever you'd like to say, then we're good. We get the result. So case 2 is what if, I see a typo here, what if they are relatively prime? So what if p does not divide m? In that case, I can use Euler's theorem. So by Euler's theorem, m to the p minus first power should be congruent to 1 mod p. Now let's think about what are our hypothesis on this e and this d. So by hypothesis from the RSA setup, ed is equivalent to 1 mod phi of n. Remember, d is like that nice inverse that undoes this exponent e. And so let's think about what does this say? This congruence right here is equivalent to saying that, well, phi of n, the modulus, should divide the difference, ed minus 1. Now think about phi of n. If n is equal to, I'll write it up here, n is pq, sorry. And so phi of n would be, well, these things are relatively prime, so that should split as phi of p times phi of q, and therefore that's equal to p minus 1. Q minus 1, and I think we wrote that out earlier in the RSA stuff too. So in particular, right, if phi of n, divides ed minus 1, well then so should each of these, right? Well, in particular, p minus 1 divides phi of n, therefore p minus 1 divides whatever phi of n divides. And so in a less confusing way, finally here, p minus 1 divides phi of n, so p minus 1 has to divide ed minus 1 also. So let's think about what does that say. Let's kind of translate that to a nice, just divisibility definition here. So if p minus 1 divides ed minus 1, that means that we can find some integer k such that p minus 1 times k gives me ed minus 1. Now what we're going to do is let's raise m to the ed minus 1 power. I'm going to use some exponent rules, and I'm just going to substitute in. ed minus 1 is the same as p minus 1 times k, and I'm using my exponent rules there. Like when you raise a power to a power, you multiply the exponents. And I wrote it this way with parentheses to emphasize that I can use Euler's theorem right now. So if I get away from the highlighting, by Euler's theorem, m to the p minus 1 is congruent to, well, 1 mod p. So you're really just raising 1 to the k, which is always just 1. So if we regroup here, if we think about what we just showed that m to the ed minus 1 is congruent to 1 mod p. Let's multiply both sides of that by m now, and of course we get m to the ed is congruent to m mod p. Let's do a concrete example with some actual numbers now too. So here's an example. There's Nikita. So she secretly picks pretty big numbers that are primes. So I looked these up. P is 2 raised to the 300th power minus 153, that's a prime, and Q is 2 raised to the 302nd power minus 267. So again, these are numbers that only Nikita knows. Those are secret. But what she does is she computes their product, and that happens to be this ginormous number right here. It's okay if everybody sees this number. Again, the idea is if you did not know any of this right here and someone just showed you that huge string of numbers, you would have no idea what the prime factorization is. And again, it would be hard for a computer to spit that out too because that number is so large. And again, in practice too, they use large numbers that are much larger than this as well. This is just as far as my brain could go tonight. So the next thing that Nikita does is, because she knows, well, here's P and here's Q, right? What would phi of n be? In other words, how many numbers are relatively prime to this? Well, she should just subtract 1 from P and subtract 1 from Q, right? That's the formula for phi of n whenever it's a product of two primes. So that if you look, that's exactly what I did. I changed 153 to 152 here, and I changed 267 to 266 right there. So Nikita knows that information very quickly. Others probably don't. Again, that's a very infeasible thing to figure out if you don't know P and Q. The next thing Nikita will do is randomly pick a number that's relatively prime to phi of n, and 5 happens to work, just playing around with it. Now what Nikita wants to do is figure out what is the inverse of 5 mod n. Remember, mod phi of n, sorry, and we'll call that d. And now I'll go to Sage, because I listed a few of these out in Sage for us already to take a look at. And so far, I have it so that we print n. You'll see that's where I got it from. So maybe what I'll do is I will try to comment this out for a minute, which is this one. And so if I ask Sage to print that out, is he going to do it? That's a good question. Maybe it's got to think for a second. Cool. Sage didn't take that long because this was too big. Everything was kind of defined above. But then now, so that's where I got the n from that I copy pasted to Notability a minute ago. And now what I'll do is I'll go ahead and I'll just show you what is d. And so notice, how did I get d? I could do that in Sage right here. The command for it is mod, and then parentheses e, which I've defined e to be 5. And then if you see p minus 1 times q minus 1, that's just phi of n, right? And I say I want the inverse of that, the multiplicative inverse, so raised to the minus first power. So if I compute that now, and I'll suppress that, there's your d. So that is the exponent that is going to decrypt things for us, essentially. Great. And so now what have we got? So Nikita is going to make her encryption function, which is what we'll call E. And what does E do? E takes an input that's some string of numbers, say, and it just raises that to the eth power, so to the 5th power, and it reduces it mod n, since everything's happening in this group z mod nz. And she's going to share that. So she's going to share this encryption function with somebody. In other words, she's going to tell you how to encrypt the message to send back to her. That's the game here. But and so everybody can see what the encryption function actually is. But what she keeps secret is what the decryption function is. And why does she keep it secret? Well, because she's the only one that knows what d is. And again, the decryption function, it just takes the input and raises it to the dth power. And so let me give you a little picture here too, a little cartoon that I drew. I probably spent way too much time drawing this cartoon, but it was kind of fun. So in the first little slide here, Nikita says, "Hey Michael, use this encryption function. E to the m is equal to m to the e mod n to talk to me, where little e here is 5 and n was that huge string above. And Michael's like, all right, yeah, fine. Cool. So on the next slide, Michael thinks to himself, I just want to send the message 123 to Nikita. So what he would do is he would take 123 and plug it into this function e, which raises it to the 5th power and reduces it mod n, in which case you get, so we've encrypted 123 as this number 281530 blah blah blah. That orange number is what he's going to send in a text or an email back to Nikita. And I've drawn a picture of the man in the middle. The man in the middle sees that. When he just looks at that, though, he has no idea how that's related to 123. It's okay that he knows that 5 is the exponent on something, but again, this is the idea of the discrete log problem. That's really hard to recover. It's harder to recover the base in this case, too. It's related to the discrete log problem. So the man is just confused. He doesn't know what that is. So Nikita gets that in her inbox or on her phone or whatever, and she can decrypt it now. What does she need to do? She needs to take that message that Michael just sent her, the 281 blah blah blah. She's going to raise it to the dth power, and when you do that, it recovers the message 123. And again, only Nikita has that D, so that is how she decrypts that message. And so what to pay attention to, Nikita basically built the whole system and just kind of shared how to use it so that anybody can now encrypt the message as she tells them to and send it to her more or less safely. And just to show you in Sage 2 how some of that works. So what did we want to do? We wanted to say m is equal to 123. And what we will do is we will print, how about mod m and modulo n to the eth power, where e is 5 still. And maybe what I'll do up here too is I'll suppress this d so it doesn't print that. Okay, and so I'm going to print this now. Oops, that name is m is not defined because I'm a dummy. I erased too much. M equals 1, 2, 3. Now let me try again. Good. And so this is the 2815 number that, again, this is how Michael encrypts 123. And then now what I wanted to show you is what happens when you raise that to the dth power. Remember, d is the multiplicative inverse of e. So I just want to show you print, I'll do it this way, mod m n to the e to the d. So Nikita has this 281 number. Now she's going to raise it to the dth power is what I'm saying. And what I expect it should give back, I expect it to give back 123. And it sure does.